All right, good morning, everybody. I'm hoping with the help of this stopwatch and Steve's sign, I can keep being on time. So thank you so much to the Skinny Atlas Lake Association and the partners who helped organize this event. My talk is above the sea surface. Most of the talk we heard today, fascinating talks, mostly about the bottom of the lake. But I'm going to talk a little bit about the top of the lake. This work is not been possible without the help of my research assistant and PhD student. The two of them are here. Sajjad, if you want to raise up your hands, and Sina as well here. Plus a bunch of other folks that are in this room that I will acknowledge at the end of these presentations. This image that you see, it is acquired or collected on September 18, 2000, or this year, by an airplane, a hyperspectral airplane from DRDC Canada, equipped with an hyperspectral sensor from Norway on an altitude of about 10,000 feet. So you can see a lot of interesting stuff on the lake. And then to be honest, I should say that this year was not the best year for remote sensing of HABs because the weather was, the situation was good, water was clear, and the Skinny Atlas Lake is a oligographic lake, which really does not work well with remote sensing stuff. We need to have a little bit of pollution in the lake to remote sensing, but we're lucky enough that we have probably the cleanest lake. So, but anyways, we tried our best to conduct a campaign of multiple organizations helping us in here with drone, satellite, airplane, boat, and labs to synthesize all this data together to understand a little bit about the formation of HABs in this beautiful lake. So I'm going to have a quick introduction of the project, and then moving to field and satellite data collection. Field data, including for water turbidity and chlorophyll A analysis. Then moving to machine learning algorithm that have been developed based on field data to monitor the lake. And then finally, using the developed machine learning, we're going to apply them to the entire lake to map the chlorophyll A and turbidity maps of the Skinny Atlas Lake on multiple days in 2025, and this is really an ongoing work. Like I said, the hyperspectral data is a very, very unique data sets that have been collected over this lake, and then we have not gotten the chance to process them yet. So that's part of the big agenda for our ongoing research. So this is really a quick snapshot of the field work that I should say field and air work that we have done, collected over the past few months. These pictures are all taken in summer 2025, just last year. We see that it's a collection of satellite, aircraft, and boat. We have made sure to have concurrent acquisition of all these data together. The satellites, such as Sentinel and Landsat, fly over our lake or our region at about 11:50 local time, and it takes probably 50 seconds for the satellite to pass over the lake. So that means that we have to make sure that we are all equipped and on the lake during that section. Obviously, the field data cannot be collected in 50 seconds, but we normally go to the lake with the research boat, with the support of Skinny Atlas Lake, the Bob, the research boat, really nice research boat, to be on the lake probably at about 11 to 3 p.m., 4 p.m., or 10 to 2 p.m., 3 p.m.-ish, to collect some 50 points across the lake, concurrent, having the satellites over at one of these points. Then also we see that these airplanes, like I said, this is the DRDC airplanes right here, that equipped with the hyperspectral sensor, flown over 10,000 feet, both on Skinny Atlas Lake and Canandaigua Lake. So the Skinny Atlas Lake was 18th of September, and Canandaigua Lake was 16th of September. We collected some really nice data sets. We've got some drone data. We have been part of a international data collection campaign. It's called ROCKX, organized by Rochester Institute of Technology. I was the PI for the water quality, but there was a bunch of some 50 organizations from other aspects of remote sensing, such as nighttime or debris monitoring and other stuff in the lake. We got this chance to have be involved in that, and these data sets would be internationally available to the researcher across the world. Moving toward the objective of the work. So you may wonder how remote sensing can help, water quality. Well, many of the research that we saw or we see day to day is based on real world field data collections. But field data are limited. You can go just so many points a year or a day, and it's very costly. Remote sensing is here to help us basically connect the dots between the field and satellite signals. So we are trying to build a model, we call it machine learning model, that build basically the relationship with the satellite, the spectral signature, with the field data. We train the model that the spectral signature of these satellite data are related to this much of turbidity or chlorophyll A that has been collected, the same position and the same point on the lake, and then build the machine learning model. So once the machine learning model is built and validated, of course, then it can be applied regardless of field work. So in any day in future, we can generate the turbidity and chlorophyll A in this case, and many other parameters of water, independent of the field day, and more importantly for the entire lake. So it's a wall-to-wall turbidity map or chlorophyll A map with a spatial resolution of few meters from across the lake. That could support a lot of research, such as the one that Dr. Mike and Dr. Chris mentioned earlier, that can be support of those. And then the ultimate goal is if we put together all this time series of this behavior of the chlorophyll A and turbidity over time, we can start seeing the behavior of the water and water parameter changes, hoping to lead us to some general conclusion about the formation of or prediction of the HAB. So that's the ultimate goal of remote sensing. So we are going to look at the past and current, and then moving to predict the future. That's the goal. So, but of course, remote sensing without field data is not. The starting point is field data. The field data that we have collected over Skinny Atlas Lake, it's some 50 waypoints across the lake. We start from north of side of the lake on the east or on the west coast all the way point 1, 2, 3, all the way to point 27, and then go back on the east side of the lake. So these are the waypoints that we have been collected every time, same points on the days that satellite data is available. So another thing that I want to mention about the satellite is satellite data. The availability of satellite data is one thing, then the non-availability of cloud is another thing. So we need to make sure that the satellite is flying over, but the cloud is not there. Plus, the wind is not there. So putting all these constraints together, make it very limited days for basically coordination of field data. But we have been lucky enough to work with a bunch of professionals that are, in the seconds of, the satellite data is flying. Well, we already know the satellite data, but the cloud is not really heavy today. Can we go tomorrow morning? Frank say, yes. So that's really the agility that we need to do this. So in this picture, you can see that, for example, this point 28 is collected at exactly the same time that the satellite has been passed over. And this is the shadow, the ghost things that you see, it's the bob that it appears in the satellite image. Well, the satellite image resolution is about 10 meters, and it's flying about 500 miles above the Earth. So it's not really high resolution, these type of freely available imagery. So before moving forward to the analysis, I'm just going to present some of the analysis of the field data, regardless of the satellite, that we have collected over these 4 major days. So these 4 days are the days that we went to the lake, collected 50 points. Well, the people, students and other personnel on 22nd of August, 3rd of November, September, 27th of August, and 18th of September. You can see that really, so this is a chlorophyll A, total chlorophyll A microgram per liter. It's really, really minor. It's pretty small, about 2 meters or 2 microgram per liter. We have a little spike here that likely is because of the nearness to the shore, which could be adjacency effect, reflection from the adjacent vegetation, because this is a 0.27 and 27 is right here, is very, very end of the bottom of the lake. So that's one of the points that probably is not representative of the chlorophyll A. And on August 27, you see a slight change or increase in chlorophyll A, not serious in terms of the HAB, but you see that the trend is more or less homogeneous across the lake. On September the 3rd, a little bit more homogeneous, meaning that probably that day has been less windy days. And then moving to 18th, when the day that we have the airplane flying over the lake, we had more of variation in chlorophyll A across the lake, from 0.2 all the way to more to toward the middle of the lake. So that's indicative of a little bit of wind or changes of variation of chlorophyll A for other reasons in the lake. Then this is the turbidity profiles of the 4 days. Again, turbidity follow the same patterns. We have less turbidity in August 22nd, then a little bit more turbidity in August 27th, then a little bit more on September 3rd, and a different variation which is similar to trends of chlorophyll A. These two measurements are independent, so you can see that chlorophyll A and turbidity on the August or on September 18 has more variation in the lake. But these are just for the 50 points on the lake. We use these points to train or the AI models here. This is a little bit of summary of the data of field data. Again, this box, the lighter box shows chlorophyll A. The chlorophyll A has a sort of a general trends of increasing all the way to August 27 and then decreasing a little bit to September 3rd, and then again a little bit increasing on September 18, but they are within a very low range, which is not indicative of HAB at all, and that confirmed with other measurement in the field as well. And turbidity, also this is the trend of turbidity. Basically, these two shouldn't be on the same page because the units are different, but we normalized the units and showed it here. So, and then interestingly, we also collected water temperature. So water temperature basically drops, of course, throughout the season from summer to fall, from late summer to early fall, and air temperature increases in this way. Interestingly, we had a pretty cold day on August 27th, but water temperature remained high. So these are just the analysis that to understand the trends of water quality with regard to the field data. Another slides, we wanted to see the correlation between turbidity and chlorophyll A. It's pretty nice correlation, about 70% of Pearson correlation between these two indices, so meaning that the more turbidity, the more, I have to, I guess, move much faster now. The more turbidity, the more chlorophyll A, and also the water temperature has an interesting relationship with chlorophyll A. Moving toward the satellite image processing, so we have raw data of the satellite. That's what you look from Google Earth probably, but the satellite data are contaminated with the atmospheric effect. This is after atmospheric corrections for the different dates, and this is a pretty cloudy day, but most of the lake is pretty basically non-cloudy. And this is the spectral signature of the water. As you see, we have a pretty homogeneous spectral signature of water on August 22nd, but we have pretty diverse spectral signature of that relate to the chlorophyll A and turbidity variation as well. So that's good indication. Another effect of satellite is the adjacency effect, meaning that in the shallower part of the lake, where the lake is adjacent to the shoreline, the spectral signature from the water that comes to the satellite is not coming directly from water, but it's reflected from vegetation to the water and go back to the satellite. That means the color really not representative of the water spectral signature, but the adjacent vegetation. This has been hugely affecting lakes, narrow lakes like this one. We have corrected this through an algorithm called Ecolite, and these are the area that has been contaminated, and this is the clear image. After all this pre-processing, we come to the developing of machine learning algorithm. We have tested a bunch of machine learning algorithms, such as linear regression and gradient boosting. We found that linear regression, in this case, pretty good result with R-squared value of 90%. That's mostly because we have limited data and nice data sets, as opposed to previous data sets that we have been used have been not basically co-registered with the satellite. Remember that these data have been collected the same day of the satellite, so that's a pretty nice correlation. Once the satellite is trained, we use, and this is for turbidity as well, so turbidity model, also we use the regression model, and then once this model is developed, it has been applied to the entire lakes for different lakes. So this is the chlorophyll A maps of the entire lake on each date. Basically, we use those 50 points, train the model, and apply the model on different dates. This is the behavior of the maps of chlorophyll A. This is another map for October and November. Also, we see pretty low turbidity, especially in November. It's very, very low turbidity or chlorophyll A. Similar trends. You can see that the average of chlorophyll A remains within below 2 microgram per liter, and then this is even way more less from September. It has been the maximum in September 19th actually. And this one is turbidity, the same map for the entire lakes. Turbidity again for the 5 dates that we have been discussing. And again, the trend of the turbidity, you can see there's a lot of information can be collected through this and being used for processing. And finally, this is the hyperspectral imagery that I mentioned. This is the hyperspectral it's not one shot, it is about 1.5 hours of imagery flight over the lake, because these are probably 3 terabytes of data sets. But this is just a snapshot, and here is just a digital elevation model of the lake. Chris showed a nicer version of this using LiDAR, but that's one is available publicly. And I just wanted to, again, we have not processed this hyperspectral data just yet, but some snapshot of different part of the lake. This is the hyperspectral imagery over 10,000 feet above the lake from, I believe this is the country club. And then you can see all these sediments loading or all this colorizing in here. It's only 3 bands, but with hyperspectral sensor, we have over 500 spectral bands, meaning that we can process and get a lot of information by analyzing these signatures. Here is the signature of the hyperspectral signature. In this case, it's near infrared bands, about 200 bands of hyperspectral signature. Again, that's going to be an ongoing research in the next few months. And I want to thank all the sponsors and collaborators of this research. It would have not been possible without all the help from the sponsors and the student and the staff involved in this research. Thank you so much.
One quick question. We have one online. This could be answered by Bahram or a few folks. So we have one question in the chat. It says, do the thermoclines circulate in the entire water column such that the oldest water is brought to the upper layers and thus circulated through the Syracuse intakes? Or is the water at the greatest depths as old as the lake itself, or trapped over a long period of time, I guess, is the question.
I believe this question is either for Mike or Chris. I didn't take care of the bottom of the lake.
So does the water stay at the bottom over years and eons,